So first up in chapter 10 is we have parametric equations. Now, setting problems up in terms of parametric equations is actually incredibly useful for describing pretty much any problem that involves motion. So what I'm going to try to do is I'm going to try to do 10.1 and 10.2 together. I'm going to talk about parametric equations in a basic sense, and then I'm going to kind of blend into doing calculus on these problems and how it changes from having regular functions of a single variable into, I guess, dealing with two functions of a single variable, since that's what parametric equations are going to end up looking like. So classically, we've been dealing with y given as a function of x. And sometimes this is actually fairly inconvenient. For example, if I have anything that fails a vertical line test, that means my y-coordinates are not given as an explicit function of x. Or, in particular, we've had section 3.5, which is implicit differentiation. We found out how to do derivatives on functions which are not necessarily given as a function of x, but how do we deal with integrals on those kinds of functions? If I have a problem which has required implicit differentiation, well, how do I attempt to apply calculus to that same problem? And in a more real sense, if I have some complicated motion, for example, if I'm trying to trace out a point on a wheel as it rolls along the ground, how do I maybe calculate the volume of the solid that that shape will form? So what parametric equations are is essentially, instead of having y as a function of x, I have both my x-coordinates and my y-coordinates given as a function of some parameter, which we usually denote with t, but we can also use r or s, depending on your handwriting. That's a really bad idea. Or maybe an angle, theta. We actually have a lot of specific math about when the parameter is an angle. And that's sections 10.3 and 10.4. So my x and my y coordinates are going to be some function of t. The book uses f's and g's, but I'm going to use x and y because I won't have to make up any new letters ever. And in some sense, we've actually already encountered parametric equations a long time ago. Because if you recall, sine of x is defined to be the y-coordinate of the circle when intersected with the angle of x. But I shouldn't use the letter x here, so let me change this to an angle theta. And similarly, cosine of theta will be the x-coordinate. So if I have a circle of radius 1, and I have an angle theta describing this line here, then what do I have? Well, on the unit circle, the x-coordinate is cosine of theta, and the y-coordinate is sine of theta. So technically, what I already have is I have a way to describe the circle using parametric equations. I will use x equal to, my x's were sines. What? No. My x's are cosines. And my y's are sines. And if I trace out the full circle, I'm going to be using theta up to 2 pi. So these create the circle. Now I can eliminate this parameter with some clever thinking. I know that sine squared plus cosine squared is equal to 1. That's one of my Pythagorean trigonometry identities. But since x is equal to cosine of theta and y is equal to sine of theta, this means that y squared plus x squared is equal to 1. That's our classic equation of the circle. But I don't need to have strange functions in order to use parametric equations, because basically any function of a single variable can already be parametrized. You just make the independent variable equal to t. What I like to do next is, what happens if I change this circle problem by just a little bit? Not function, but curve. Let's suppose I have x equal to 2 sine of t and y equal to 3 sine of t, and I'm going to let the parameter t run from 0 to 2 pi. What's the curve that I'm going to sketch out using these parametric equations? Well, that could be difficult to determine since we're so used to dealing with regular functions of a single variable. But I could try to think about them. So my x's in terms of t are going to look something like, let's see, I'm going to go from 2 as a maximum and negative 2 as a minimum. Now from sine, that means I go up and then down. We'll pretend that that looks good. But if I do y's, I'm actually going to go to negative 3 up to positive 3. And it's going to start at the top because it's cosine. So it's going to be up here, down there, down here, up here, and back up to here again. So how should I read this? Well, I should read this as my x values, they start at 0, they go over to 2, then they go back to 0 and back to -2, and then they come back up to 0. My y values start at a maximum of 3, they go down to 0, down to -3, and then back up to where I started. And these are happening at the same time. So if I try to trace out based on these funky arrows I just drew, I should expect let's see here. From 0 to 2, when x is maximum, y is 0. Because when x goes up to 2, that's at pi over 2, but at pi over 2, my y's are equal to 0. So, plotting these is basically going to be kind of a little bit of guesswork and a bit of plotting points. But x starts at 0, but my y's start at 3. Then my x values are increasing up to 2, while my y values decrease down to 0. Then my x values decrease to 2, while my y values decrease to -3. And then I end up going back. So what this looks like is it looks like it could be an ellipse. Because what I expect for a circle is if these were both had a coefficient of 2, for example, if they had the same coefficient, then I would expect to have gotten a circle of radius 2, because x would be equal to r sine of t, and y would be equal to r cosine of t. Of course, it wouldn't be the standard setup of the circle. This is actually moving in an opposite direction as we're used to for angles. But how can I verify that it's an ellipse? Well, ellipses must satisfy x squared over a squared plus y squared over b squared equal to 1 for something. So what kind of appropriate choices can I make? Well, the easiest way for me to go about it is to choose a and b so that they eliminate the coefficients on my parameters. So if I plug my parametric into this equation, my x was 2 sine of t, so this is 2 sine of t squared divided by a squared plus 3 cosine of t squared divided by b squared equal to 1. So if I choose a and b to be, let's see, 2 and 3, that means x squared over 4 plus y squared over 9 equal to 1. This is an ellipse with a major axis along the y-axis with a radius of 3 and a minor axis along the x-axis with a radius of 2. Well, this is equivalent to 2 sine of t squared divided by 4 plus 3 cosine of t squared divided by 9 plus equals 1. But if I rewrite this, I have 4 sine squared of t over 4 plus 9 cosine squared of t over 9 equals 1. And this is a true identity. Which means that these parametric equations satisfy the definition of an ellipse, or the necessary formula for an ellipse. Sometimes, though, I mean, this example right here was essentially why we did the conic sections, or why we're doing the conic sections in Calculus 2, is because hyperbolics and ellipses and things are very easy to translate to and from parametric equations by using appropriate trigonometric functions. Ellipses, for example, are just going to use sine and cosine, but hyperbolas are going to use secant and tangent, or cosecant and cotangent. So if I recall one of the functions for a hyperbola, the only difference between having a negative x or a negative y is which of x or y gets to be secant, basically. Well, what satisfies this one is I'm supposed to look at this kind of like secant squared of t minus tangent squared of t equals 1, or cosecant squared of t minus cotangent squared of t equals 1. And this would be the case where secant of t is equal to x over a, and tangent of t is equal to y over b, or similarly for cosecant and cotangent. But not all parametric equations are going to be conic sections. And certainly not all of my parametric equations are going to involve trigonometry. So just to kind of ruin exactly what I just said, why don't we look at x equal to cosine of t and y equal to sine of t. Nope. I actually want sine of 2t. How would I try to eliminate the parameter for this? Now, what we mean when we say eliminate the parameter is I want to rewrite this as a function of a single variable. I don't want to involve a parameter. I want to see what it looks like without the t. Well, that's a little bit more difficult because we don't have some kind of a trig identity relating sine of 2t with cosine of t. Well, sine of 2t is a double angle identity, so this is 2 sine of t cosine of t. But what I notice here is I got a cosine of t, which is exactly my x. So I have 2 sine of t times x, basically. So all I can do really is try to replace the sine with something, and I'm going to have to use x, or the Pythagorean identities, to try to do that. So let's see. Sine squared of t plus cosine squared of t is equal to 1, which means sine of t is equal to the square root of 1 minus cosine of t squared. Which means that my sine of t is actually equal to the square root of 1 minus x squared. Now what we've lost in doing this process of eliminating the parameter is we have lost the negative half of our function. See, this should be a plus or a minus, and this should be a plus or a minus, which means I could write y equals plus or minus 2x square root 1 minus x squared, which doesn't look great. Alternatively, if I was okay with some implicit looking functions, I could have said that x squared equals sine squared of t, and y squared equals 2 sine squared of t cosine squared of t, which you'll notice I'm just going to end up with the square of what I had on the right. So this is y squared equals 4x squared times 1 minus x squared. This is actually a fun one to graph if you look this one up in the book. I believe it's one of the examples. This is a self-intersecting curve. Now, essentially what happened is since the y value races through its coordinates twice as fast as the x value does, the result you get is kind of like if you took a circle and you twisted it. Kind of like when you twist a rubber band. So, what it should end up looking like is you start here, you go up, and then down, and up, and then, whoa, that aren't. You go up, and then down, and then up, and then down, and then back up again. So we see here we have a self-intersection. So we'll get back to this self-intersecting problem with a different example later, but just to look ahead is when I'm looking for slopes, I'm not necessarily looking for slopes at points with parametric curves. I'm looking for slopes at times, where we're just using t for time. So even though I have an intersection, if I try to determine the slope at the point of this curve, I am going to get confused. But I do have only a unique slope at a time at this point, depending on which part of my parametric curve I am working on. If I'm working on an earlier time or a later time. Sometimes, though, all we have to do to eliminate a parameter is to just simply solve for t without trying to think too hard. So here I could probably set up x to be a function of y, but I would much rather set up y to be a function of x, because y here is already a square root, and I won't accidentally double up on my times or anything. I've kind of been cheating a little bit, because anytime you have a set of parametric equations, you should also include the bounds on which the parameter is defined, and I've just kind of been ignoring those. So here I have from x, t is equal to x minus 7, which means y is equal to the square root of x minus 7 plus 2. But something I promised is that parametric equations are really good for motion. In particular, component motion. If different components of your motion operate independently of one another, then you can simply combine them using separate sets of parametric equations. They kind of compose and just add together. So the example I'm going to do is the cycloid, which is the same thing as tracing a point on a wheel as it rolls along the ground. But other things you might be able to do, and I encourage, is try to find a circle of radius. Try to find the curve in parametric form traced out by a point on a wheel which is rolling around another wheel of a larger radius, or possibly smaller. You do what you want. Another situation you might consider is motion in space. So the parametric equations are capable of tracking the x and y coordinates separately of an object in motion. So two examples I can think of off the top of my head. One, you have a cannonball. These are very easy to describe in terms of horizontal and vertical vectors, which is the same thing as dealing with x coordinate and y coordinate parametric equations. So if I fire something out of a cannon, I can track the height using our standard Newtonian physics problems, and then I can track the x coordinate, or the distance the projectile follows, simply by finding the horizontal component of the force and multiplying that by whatever parameter. Or also, if you have motion in space, if you are in some kind of a vehicle which is providing constant velocity or acceleration, and you are turning this vehicle according to some kind of function, then you can describe using parameters your exact position simply by applying your constant force separately to your parametric equations, which determine your direction. So what we're doing now is the cycloid. We'll suppose a spot is marked on the edge of a wheel. I want to find parametric equations that describe the path of this marked spot. So for simplicity, I'm going to start with the spot on the ground. Then as the wheel rolls without slipping, let's add that, no slipping, the spot is going to be at a different height relative to the ground. So what I want to do is first I want to notice that, well, since this is rolling, depending on my frame of reference, I'm going to see some different things. So first I'm going to pretend that Earth is the center of the universe. It's really a standard assumption. We're also assuming that it's flat, by the way. And what I'll do is I'll try to track the position of the dot as I'm rolling. So after a little bit of rolling, my dot is going to move, which way is it rolling? It's rolling that way. So my dot is going to be moving clockwise around the center of my wheel. So I'm going to set this up to describe it in terms of the angle by which it has moved. So the key here is I'm going to be talking relative to the center. You know, that's not alarming enough. relative to the center. This is my Earth is the center of the universe assumption. The spot follows some parametric equations. So let's see. The x starts at 0 relative to the center. The y starts at, let's see, what's my radius? I didn't label my picture. Radius 2. So the y starts at -2. After a quarter of rotation, after pi over 2 radians, the x is at -2, and the y is at 0. So I'm going to see if I can use this to set up a couple of parametric equations, because I know I'm going to be using sine and cosine somehow. So it looks like, since y starts at -2 and then goes up to 0, I'm going to use y equal to negative cosine of, we'll use theta. And then x, it starts at 0 and then it goes down to -2, which means I'm going to be using x equal to negative sine of theta. Now you notice here I did not include any information about the rate at which theta is changing. So technically this problem will be described in terms of how many revolutions have occurred for my x and y coordinates. So these are my x and y coordinates relative to the center. So since those are relative to the center, I should find out where my center is going to be. Well, if my wheel of radius 2 makes one full revolution, how far will the wheel have traveled? Well, one full revolution rolling along the ground is going to be one whole circumference. Or, the center of the wheel will have moved by, the circumference is 2 pi r, so this is 4 pi. And this is for 2 pi radians of rotation. Now, if I assume my wheel is rolling at a constant rate, then my x-coordinate is going to be changing at a constant rate. Now, my x-coordinate has changed from 0 to 4 pi in 2 pi radians. Now, so if this is a linear relationship, I'll be using x equal to, let's label this is just the center. X would be equal to 4 pi divided by 2 pi radians, which is equal to 2 theta. And my y-coordinate, well, as long as my wheel is rolling along a flat ground, my y-coordinate shouldn't be changing at all for the center of the wheel, since wheels are round. If my wheel was an ellipse, I would have a much more difficult problem. So this means y is going to be constantly equal to 2. Since it's a radius of 2, the center of the wheel will be constantly 2 whatevers off of the ground. Which means my component motion can combine I know the x and y coordinates of the dot relative to the center, and I know the position of the center. So what's going to happen is I'm going to just follow the center, and I'm going to add or subtract a little bit depending on the values I get from sine and cosine for the relative part of the problem. So I have 2 times theta minus, what did I use? Sine of theta. And y will be 2 minus cosine of theta. Now, depending on how you start this problem, you might get things which look a little bit different. Maybe if you started with the wheel at the top, you'll have switched the sine to the cosine. If the wheel is rolling in the opposite direction, then maybe the signs will change. And this would be true for theta greater than 0. Well, it's also true for theta less than 0 if I start rolling backwards. So my question is, what if I applied a speed to this wheel? So let's suppose that this wheel is rolling along, that it's rolling along at 4 feet per second. That means I should follow my x coordinate for my center amount of work to try to find out what theta will be in terms of time, t. So on the one hand, from the parametric equation, from the center, I have x is equal to 2 times theta. From the speed setup, I know that x should be equal to 4 times t. So if I set these equal to each other, or I combine them, and I have that 2 theta should be equal to 4t. For example, if 1 second has elapsed, then my wheel will have, the center of the wheel will have traveled 4 feet, and that corresponds to a number of radians which have been revolved. Or if I were to set a particular angle, I can find out how much time it took to roll that far. So this means that theta is equal to 2t, and I can rewrite my parametric equations as 4t minus sine of 2t, and y equals 2 minus cosine of 2t. And this would be for t greater than 0 as well. Only this time my parametric equations come with units. So my challenge to you guys, use the notions of component motion to find parametric equations describing the path of a radius 1 wheel revolving around a radius 10 wheel. So again, no slipping allowed. What you should get at the end of this is something that looks a lot like a flower. So moving on to the calculus part, we're going to just kind of race through chapters, well, just chapter 3, I guess. Well, 3, 4, and 5. If I'm talking about derivatives, the slope of a line, or the slope at a point on a curve is, and always will be, dy over dx. And that's my rise over run if I'm dealing with the Cartesian coordinate system. However, there are two places I can talk about having a slope of 0. If I want a maximal height type of situation, this means that dy dx is equal to 0, or specifically, dy dt is equal to 0, and dx dt is not equal to 0. And the reason for that actually kind of goes back to chain rule, is because dy over dx is equal to dy dt divided by dx dt. So that's a horizontal tangent line. That's when I'm going to rewrite this. I'm going to say x prime of t is not equal to 0, y prime of t is equal to 0. Since we're dealing with parametric equations, the ddx notation is no longer going to be totally helpful. If I want vertical tangents, then what am I going to have? I'm going to have y prime of t is not equal to 0, but my x prime of t is equal to 0. But what happens if I have both? If x prime of t is equal to y prime of t, and they're both equal to 0, then what happens is you're going to have a cusp. You might not always have a cusp, depending on the particular values, in which case you're going to have to find a limit, but generally you're going to end up with a cusp. And the reason for that is the x's are going like that, the y's are going like that, so what happens is you're going towards the spot and then away from the spot. So a lot of times this will end up looking like this, or in the case of the cycloid and previously, you end up with these large humps, where here you get to dx dt equals 0, because that's where it dips down and back up again, and the dy dt is equal to 0, because that's when it hits the bottom and then starts going back up again. It is entirely possible that you won't have a cusp. You can come up to a point, have a slope of 0, and then move on. But that's a silly example, because this occurs when x and y are kind of the same thing. So you always got to be careful when looking for your specific tangent lines that you're not accidentally dividing a 0 divided by 0, because those end up in cusps, and you won't have a tangent line for that one. And if we want areas, normally what did we do? Well, we found a little change in x, and we multiplied it by a height, right? But what we're doing now in parametric is my x values are now a function of t. And so I have a little bit of chain rule built in, because my change in x corresponds to a change in t, and everything is a function of t. So the area will actually be equal to the integral in t from, we'll say, t1 up to t2. Instead of having y values, we have y of t. And instead of having dx's, we have x prime of t dt. In general, all of my integrals look like this if I'm turning them into parametrics. It's because my change in x's, my x's are now functions of t, so my change in x's are now change in t values. Or they're now a change in function values which are dependent on a change in t values. But the benefit of parametric is now it's really easy if I need to find volume in a different, or area in a different direction, so to speak. Because now I can just do x of t times y prime of t dt. So the first one was similar to the integral from a to b of f of x dx. And the second one is similar to an integral from c to d of g of y dy. See, if I didn't include the x prime of t here, then my Riemann sums would not be accurately describing the widths of the rectangles as they existed on the graph. I would have a width in t values, but I wouldn't have the correct width in x values. So I would be finding some kind of an area, but it wouldn't be the area that exists on the paper. Now similarly, arc length, I missed doing a video on that, so let me go ahead and describe this. Arc length was made by approximating using secant lines. And what we essentially got was a delta s, a delta x, and a delta y, where the delta s was equal to the square root of delta x squared plus delta y squared. And this translated into a ds, which could be either equal to the square root of 1 plus y prime squared dx, or an x prime squared plus 1 dy. But what I'm going to do is I'm going to translate that into parametric, where the x primes and the y primes, they just kind of stayed there, but they're both now functions of t. So for the same reason that, or the same way that this ds was created in parametric, we're going to use ds equal to square root of x prime squared plus y prime squared dt. Or in terms of deltas from before, I would have delta x over delta t squared plus delta x over, delta y over delta t squared multiplied by delta t. So you can see how that distributes in to be just how we like it. So as usual, arc length is just simply the integral ds, except now it's going to be t1 to t2. But since ds only has one form, because we don't have to solve for any functions in terms of other variables, this is just the integral x prime of t squared plus y prime of t squared dt. And similarly, our arc length, our surface areas of revolution, is going to be an integral from t1 to t2 of 2 pi y of t ds for parallel to the x-axis, and 2 pi integral from t1 to t2 of x of t ds for parallel to the y-axis. So a similar challenge from this video determine integral formulas for volumes of revolution. Now, I just tossed a bunch of stuff on you guys, so I want to actually do one of these that I've chosen. So we want to consider the curve defined by the parametric equations x equal to t cubed minus 12t and y equal to t squared. And that's for all t values. So first what I'd like to do is draw a sketch of this, because I need a picture of what I'm looking at to determine whether or not I'm doing some of the later work correctly at all. Now my y-coordinate suggests there's going to be some kind of symmetry involved, but I don't want to make any huge leaps of faith, so I'm just going to try to graph it normally. I'm going to look for some of the same things we normally look at, like from chapter 4. I want to find some x and y intercepts. I'd like to find some horizontal and vertical tangents. And I'd maybe like to determine I'm going to include t equals 0 here just because I'd like to know where I'm starting. But I'd also like to determine extreme values. I want to know what happens when t goes off to infinity. Well, I already know what happens when t goes off to infinity. If t goes to infinity, well, both x and y are going to go off towards infinity. And the same thing for negative infinity. They'll both be infinite, but the y will be positive. Because I don't have finite endpoints for my t interval. So x-intercepts, that's when y is equal to 0. So if y is equal to t squared is equal to 0, that means t is equal to 0. Great. But that's when the x-intercept occurs. It does not tell us where the x-intercept is. That's at x of 0, which is actually, again, at 0 minus 0, which is 0. That's the only one for x-intercepts. Y-intercepts, when x equals 0, so that's when x is equal to t cubed minus 12t equals 0. I can factor this. I get t equal to, factoring. T multiplied by t squared minus 12 equals 0, which means t is equal to 0, or t is equal to the square root of 12, which is plus or minus 2 root 3. Now again, these are when the y-intercepts occur. It does not tell us where the y-intercepts occur. So I'll plug these into y. where this is y equal to, no, I want y of 0, which is 0. So that's good because that should have happened up above. But also want y of 2 root 3 and y of negative 2 root 3. But when I square these, the same thing is going to happen. I'm going to get 12 and I'm going to get 12. Which means I have two y-intercepts of 12 at different times. So I know right now that this is going to be a self-intersecting curve. So I should also find, maybe I can squeeze that in right over here. Let's find horizontal tangents. That's when y prime of t is equal to 0 and x prime of t must not be 0. But y prime of t is equal to t squared. No. Y is equal to t squared. So y prime of t is equal to 2t, which happens when t is equal to 0. So I know that at my origin, at my x and y intercept of 0, 0, I'm going to have a horizontal tangent line. Because I already know what happens at t equals 0. Vertical tangents. That's when x prime of t is equal to 0 and y prime of t must not be 0. But x prime of t is equal to 3t squared minus 12. And if that's equal to 0, that means that t squared is equal to 4. Yes. Which means that t is equal to positive or negative 2. So I have vertical tangents when t is equal to positive or negative 2. So where those vertical tangents are has to be determined by plugging them back into the parametric equations. So x of 2 and y of 2 is equal to, let's see, x of 2 is 8 minus 24, and y of 2 is equal to 4. Those are big numbers. X of minus 2 is equal to minus 8 plus 24, so that's a positive 16, and y of negative 2 is again equal to 4. So let's try to get a sketch of what happens on this graph, or on this curve. So I know at the origin, I never got any negative numbers for y values, and I shouldn't, because y is equal to t squared. That's a square. I know that at t equals 0, I'm at the origin. Now, if I go up to t equals 2, I have vertical tangent lines. Oh, I also know that it's flat down here, so something like that. But I have vertical tangents at t equals 2, which is a y-coordinate of 4 and an x-coordinate of positive and negative 16. So I guess we'll make this 4 and this 16. And the opposite side, a negative 16. So I've got vertical tangents here and here. Horizontal tangent down there. So this is a pretty wide picture. I have a y-intercept, additional y-intercepts. At y equal to 12 when t is equal to 2 root 3 and negative 2 root 3. but I have 2 of them, so I should try to determine where they're coming from. Now, the square root of 3 is, of course, bigger than 1, so these occur before and after my vertical tangents, so I should be careful about those. From t equals 0, I got a vertical tangent of x at x equal to minus 16 at t equals 2, and then at t equal to 2 root 3, I ended up here. Let me put that somewhere else. Which suggests that my picture is going to go something like this. And I'm moving in a forward direction here because my t values are increasing. But I also have a vertical tangent at t equal to negative 2 over here. So I should attempt to mirror this. I've got cables being difficult here, so let's see if I can pull this off. And I'm coming from these locations. So these should be pointing towards, oh geez. So they should be pointing towards my t equals 0. Let's see if I get rid of this arrow. So what I have for this problem is I have a self-intersecting curve. On the approach, I have t equal to negative 2 root 3, and then t equal to negative 2 over here. Then I get to t equals 0, up to t equals 2, and back to intersect itself again at t equal to the square root of, or t equal to 2 square root of 3. Now, there's a nice filled-in loop here, and I would like to find out the area of that loop. Now, it seems like this would be really difficult to describe using vertical rectangles. So I'm going to use horizontal rectangles. And I'm going to specifically try not to subtract the function from itself, because if I try to do a long horizontal rectangle, I'm going to be trying to take t equal to negative 2 minus t equal to 2. Right? Right. But if I do it again later, what are these values? T equal to what minus t equal to what? Is it simply the positive or negative version? How do I write that into an integral? See, that's difficult. So what I'll do, to find the area contained in the loop, I have y-intercepts at t equal to negative 2 root 3, t equals 0, and t equal to 2 root 3. So I'm going to treat this like I have 2 lumps on a regular graph. I'm going to find the integral from negative 2 root 3 up to 0. I'll find that area, dt, and then I'll find the integral from 0 to 2 root 3. I'll find that area, and I'll just add it together. But how do I find the area? Well, it's the long width of these rectangles multiplied by the tiny height of the rectangle. So this is going to be x of t for the heights and a y prime of t for the widths. Or I've kind of flipped my words, but the long side of the rectangle will be x of t, and the short delta y version for the width of the rectangles is going to be y prime. And similarly over here, I'll have x of t times y prime of t. It turns out this is easy to do. because x of t is just t cubed minus 12t, but y prime of t is 2t dt plus the integral from 0 to 2 root 3. Same thing. So it seems like this time it's safe for me to just combine these integrals into one. But just to be on the safe side, I'm not going to do that. So this is equal to the integral from negative 2 root 3 to 0, 2t to the fourth minus 24t squared. Now, I'm going to save ourselves some trouble here. This is an odd function. So what I'm going to get is, I'll get minus, I'll call this big F of negative 2 root 3. Because if I plug in 0, I get 0. Plus big F of 2 root 3 minus 0. But since this is an odd function, I have odd powers here. Since this is an odd function, the negative will distribute in and out of odd functions. So this is actually equal to 2 times big F of 2 root 3, which is just an awful number, I'm sure. So I have 4 times 2 root 3 to the 5th over 5 minus 16 times 2 root 3 cubed, whatever that volume is. Now, some of you may be asking, well, heck, why didn't those areas cancel out? Because from this direction, my dy's were negative, and my x's were positive. Versus in this direction, my delta y's were positive, but my x's were negative. So technically, all those errors were kind of already accounted for. So they wouldn't have automatically canceled out. But what I did end up getting is likely a negative answer because something was negative for the whole part of my integral. So what I should amend, total area will be the integral from t1 to t2 of the absolute value of y of t x prime of t dt. The absolute value is there because, as in my picture, I could have negatives from the dy, which is kind of like doing an integral backwards in the regular functions of one variable, or I could have negatives for my x values, which is the same thing as having taking the integral of an area which lies below the x-axis, which actually gives me a negative value. For the sake of time, I will not actually fill out arc length or surface area integrals because the process by which they work is the same. You should draw your picture because your integrals are going to be in terms of t values, and so you need to draw your picture to determine exactly where your t bounds are going to be. The x and y bounds might be easy to determine, but the t bounds are the ones that matter. And don't forget, when you're trying to graph these things, if you solve for a t value, that's not the point you're plotting. You need to plug that t value back into the parametric equations to get the associated x and y coordinates before you plot them.